Right now, Earth carries you around the sun near 100,000 kilometers per hour. Tonight we share 100 calm space facts, starting with the moon, about a second of light away, gently changing. If you want learning, comment what you want explained. If you're here for sleep, type sleep. Replays help. Your note sets the pace. Let's make space feel calm and measurable with distances that your mind can rest on. When scale feels steady, the imagination has fewer sharp edges to hold on to. We'll build a gentle ladder, starting close, then stepping outward one calm rung at a time. First rung, the length from your hand to your elbow, a simple human distance. Next rung, the size of a room where sound and light feel familiar. Then a city where a drive becomes a map in your mind. Now the planet beneath you, round and quietly enormous. Earth is about 12,700 kilometers wide, from one side to the other. If you could walk that line, it would feel endless, but it is still a single object. From space, Earth is not a place you stand on, but a sphere you travel with. Pause and picture Earth as a dark marble with a thin blue breath of air. The next stop is our nearest neighbor, the moon, hanging in the same night. The moon is about 384,000 kilometers away on average. Light crosses that gap in about 1.25 seconds. So when you see moonlight, you are seeing a moment that is just barely in the past. Even the moon, close as it feels, is far enough to make space feel real. Now widen to the sun, the warm lamp of our entire sky. The sun is about 150 million kilometers from Earth on average. Light takes a little over 8 minutes to reach us from the sun, so sunlight is a soft message arriving after an 8-minute journey. If the sun changed right now, we would notice only after those minutes passed. That delay is not dramatic, just a reminder that distance has a gentle cost. A light minute is simply how far light travels in 1 minute. A light year is the same idea, stretched across a year of travel. These are distances, not time machines, and they help us keep our footing. Now, let's add motion, because distance and motion are always holding hands. You may feel still, but you are moving through space in smooth layers. The first layer is Earth's rotation, turning day into night like a slow wheel. At the equator, that spin is about 1,670 kilometers per hour. Farther from the equator, the spin is gentler because the circle is smaller. You do not feel that speed because it is steady, like a train gliding smoothly. What you feel is change in speed, called acceleration, not constant motion. The next layer is Earth's orbit around the sun, a wide, quiet loop. Earth moves around the sun at about 30 kilometers per second. That is about 107,000 kilometers per hour. Steady and continuous. Again, it does not press on you because the motion is smooth and shared. Later, we'll link this calm shared falling to why astronauts feel weightless nearby. Now add one more layer. The sun itself is moving through the galaxy. Our sun circles the Milky Way at roughly 220 kilometers per second. One trip around takes about 230 million years. In that time, continents drift, mountains rise, and life slowly rewrites itself. And through it all, the sun keeps its patient pace, carrying us along. Pause for a breath, and let that layered motion feel like a slow river. To keep distances simple, astronomers use a friendly yardstick. It is called the astronomical unit, or AU. The average sun to Earth distance. 1 AU is about 150 million kilometers. We use an average because Earth's orbit is not a perfect circle. It is a gentle oval, called an ellipse, with the sun slightly off-center. The closest point is called perihelion when Earth is a bit nearer the sun. The farthest point is called aphelion, when Earth is a bit farther away. This change is only a few million kilometers, small compared to the whole orbit. It is not what makes seasons. Seasons come mostly from Earth's tilted axis. Still, the changing distance is real. A soft inhale and exhale of the orbit. Now a scale trick, so your mind can hold the solar system in one image. Imagine Earth as a peppercorn, small enough to sit on your fingertip. In that model, the sun is like a grapefruit, bright and hefty. The peppercorn Earth would orbit far across a large room from the grapefruit sun. Space between is mostly empty, not because it is wasted, but because it is vast. And the moon, in that model, would sit a short step from the peppercorn. These models are not perfect, but they make the spacing feel honest. Now, let's step beyond the planets into our wider neighborhood. The solar system is not a sharp edge, but it does have a kind of boundary. The sun blows a steady stream of particles called the solar wind. That wind forms a bubble around us, pushing into the thin gas between stars. The outer region of that bubble is called the heliosphere. Far out, the solar wind slows and meets the surrounding interstellar medium. That meeting region is near the heliopause, a practical edge of the sun's reach. Spacecraft, like Voyager, have traveled far enough to sample that outer realm. Distances out there are often counted in astronomical units, not kilometers. Pluto's average distance is about 40 astronomical units from the sun. The heliopause is far beyond that, over 100 astronomical units away. Even so, this is still a tiny porch compared to the neighborhood of stars. Now take a longer step to the nearest stellar neighbors beyond the sun. The closest star system is Alpha Centauri, a few light years away. A few light years means light needs a few years to cross that space. It is a simple idea, and it keeps our scale grounded. When we look far, we are also looking back in time, gently and automatically. Now zoom out again until the stars become a faint, milky band. That band is our galaxy, the Milky Way, seen from inside its disk. We live in a thin, wide disk of stars, with a thicker, puffier halo around it. When you look along the disk, your view passes through more stars and dust. That is why the Milky Way looks brighter in a long, soft streak. The Milky Way is about 100,000 light years across, give or take. Our sun sits far from the center, in the quieter suburbs of the disk. And the galaxy is not alone. It belongs to a small family called the local group. Beyond that are clusters and filaments, like a cosmic web woven in slow motion. Now for a calming idea. The universe has horizons, not walls. There may be more universe than we can ever see, and that is okay. We can only observe what light has had time to reach us. And space itself has been expanding, stretching distances as light travels. So the observable universe is a region we can see, not the whole story. Its radius is about 46 billion light years, much larger than its age suggests. That is because space expanded while the light was on its way. This is not a chase scene. It is a quiet unfolding over billions of years. Hold the idea of look-back time. Distant galaxies appear as earlier versions of themselves. The farther the light travels, the younger the universe looks in that direction. Later, you'll hear why the oldest light is still here, filling space like a soft glow. For now, return to your ladder and notice how steady it feels. Arm's length becomes room, room becomes city, city becomes Earth, Earth becomes moon, moon becomes sun, sun becomes a galaxy of stars. And beyond that, a horizon made of light, time, and gentle expansion. If you like, pause and picture a quiet line stretching outward, stop by stop. Which step felt easiest to imagine? The moon, the sun, or the Milky Way? Keep that answer softly in mind, because it will help the next facts land. Now that distance feels tangible, let's look at the gentle tools that turn faint light into knowledge. Space is mostly unreachable, but it is not unknowable. The universe sends us messages, and most arrive as light. Light is not only brightness, it carries structure, color, and fine detail. Think of light as a letter with a return address and a gentle signature. When we spread light out, we get a spectrum like a soft rainbow. A spectrum is not a mystery code, more like a calm barcode. It is a pattern that repeats, and patterns are easy for science to trust. Some spectra look smooth, like a gradient with no breaks. Other spectra have thin dark gaps, where certain colors are missing. Those gaps are called absorption lines, and they matter a lot. They form when atoms in a cooler gas absorb specific wavelengths. Each element absorbs its own set of wavelengths, like a unique fingerprint. Hydrogen has a familiar pattern, and so does helium. Sodium leaves a strong mark too, and iron leaves many fine marks. We can measure those same patterns in laboratories on Earth. When we see the same pattern in a star, we can name the element there. That is how we know stars contain many of the same atoms we do. Sometimes we see bright lines instead of dark ones. Those are emission lines, made when hot gas glows at specific wavelengths. Nebulae often show emission lines, like gentle lanterns in space. So a spectrum can tell us composition, temperature, and even density hints. Color also carries a calm clue about temperature. Hotter objects tend to peak in bluer light, cooler ones in redder light. This is related to how warm objects radiate energy across wavelengths. But our eyes are not perfect thermometers. Cameras and screens can shift color, and processing can exaggerate it. So astronomers use measured wavelengths, not just pretty images. They compare the spectrum's shape and its peak, not the mood of a photo. Even then, the story is careful, with ranges rather than single numbers. This is where uncertainty becomes a friend, not a flaw. Astronomers often include error bars, which are honesty made visible. An error bar says, "This is our best estimate within a known margin." That habit keeps the whole field steady and self-correcting. Now, beyond what something is, we also want to know how far it is. For nearby stars, distance can come from gentle geometry. The method is called parallax, a slow shift in apparent position. It is the same effect you see when you close one eye, then the other. Nearby objects shift against a distant background more than far objects do. In space, the baseline is Earth's orbit, measured across the year. Astronomers take careful images months apart and measure tiny shifts. These shifts are small, like a hair's width seen from far away. So parallax needs precision, patience, and stable instruments. When parallax works, it gives a direct distance without extra assumptions. Farther out, parallax becomes too small to measure well. Then, astronomers use distance markers that act like mileposts. Some stars brighten and dim in a regular rhythm. Cepheid variable stars have a link between their period and true brightness. If we know true brightness and we measure apparent brightness, we infer distance. It is like judging how far a lantern is by how faint it appears. For even larger distances, some supernovae help. Certain white dwarf explosions reach similar peak brightness each time. These are used as standard candles across galaxies. They are not perfect, so calibration and uncertainty stay important. Each rung of distance builds on the rung before it. That ladder is how we map a universe we cannot step across. Now let's talk about motion, because light also reveals movement. If a source moves toward us, its wavelengths shift slightly shorter. If it moves away, its wavelengths shift slightly longer. This is called the Doppler effect, and it is very quiet but powerful. It is similar to how a siren's pitch changes as it passes you. In light, we measure the shift by tracking spectral lines. A line that should sit at one wavelength appears nudged to another. That nudge tells us speed along our line of sight. Over time, these shifts can reveal an orbiting pattern. A star can wobble because a planet tugs on it. The star's light then shifts back and forth in a tiny rhythm. This is the radial velocity method, and it found many early exoplanets. It is most sensitive to massive planets that orbit close to their stars. That is a detection bias, and it shapes what we find first. Bias does not mean wrong. It means the catalog is incomplete in a known way. Another major method watches starlight dim, just slightly, now and then. If a planet crosses in front of its star, brightness dips for a short time. This is the transit method, like a moth passing a porch light. The depth of the dip hints at the planet's size compared to the star. The spacing between dips reveals the planet's orbital period. The duration and shape of the dip can hint at the orbit's tilt and speed. With many transits, we can refine the planet's size very carefully. If we combine transit size with radial velocity mass, we can estimate density. Density tells us if a world is likely rocky, icy, or gas-rich. Sometimes, during a transit, a little starlight filters through an atmosphere. That filtered light can carry extra spectral fingerprints. It can hint at molecules like water vapor, carbon dioxide, or methane. These are difficult measurements, and they come with careful uncertainty. Again, the calm theme is consistency, not drama. Now, step back and notice the pattern. We learn from spectra, geometry, timing, and tiny shifts. Most of it is patient watching, repeated until the noise settles down. Telescopes are the tools that make faint signals readable. A larger mirror or dish collects more light, like a wider bucket in rain. More collected light means fainter objects become visible. Resolution matters too, which is how fine a detail we can separate. In simple terms, bigger optics can see sharper if the system is steady. But Earth's atmosphere blurs some details, like looking through moving water. It also blocks certain wavelengths almost completely. Most ultraviolet light is absorbed before it reaches the ground. X-rays and gamma rays are blocked too, which protects life. Much of the infrared is absorbed by water vapor in the air, so we place some telescopes high in dry places to reduce absorption. And we place others in space above the atmosphere entirely. Different wavelengths reveal different stories about the same object. Radio waves can pass through dust that blocks visible light. Infrared can show warm dust and young stars in hidden nurseries. Ultraviolet highlights hot, energetic regions. X-rays trace extreme environments like shock waves and hot plasma. So astronomy is really many astronomies layered together. Sometimes we want a telescope larger than we can build as one piece. That is where interferometry comes in. Calm teamwork between instruments. By combining signals from separate telescopes, we mimic a larger one. Radio arrays do this beautifully spread across wide landscapes. The result is a virtual telescope with very fine detail. It is like making one sharp ear from many quiet microphones. Now, light is not the only messenger in the universe. Some messages arrive as particles that rarely interact with matter. Neutrinos are one example, streaming from the sun's core. They pass through Earth almost untouched, like ghosts of fusion. Detecting them is hard, but they confirm what is happening inside the sun. They helped verify that the sun shines by nuclear fusion. There are also messages carried by gravity itself. Gravitational waves are ripples in spacetime from massive accelerating objects. They were detected as tiny changes in distance measured by lasers. One observatory is the Laser Interferometer Gravitational Wave Observatory, or LIGO. It can sense changes smaller than an atom across long arms of light. Those waves have come from merging black holes and neutron stars. In the dense Remnants section, we will connect those waves to the objects that made them. For now, let it feel simple. The universe speaks in many quiet languages. Light is the most familiar, but it is not alone. And every method has limits, which is why astronomers compare methods. Cross-checking keeps the map steady, even when the signals are faint. If you like, pause and choose what feels most intuitive. Is it geometry, spectra, or timing? Hold that choice gently, because it will guide how the next chapters land. With the measuring tools in mind, we can meet the closest star and its steady, flowing power. Now, we meet the sun, the nearest star, and the source of most warmth on Earth. It looks steady from here, but its atmosphere is always in motion. the sun is mostly hydrogen, with helium as the next most common ingredient. Those simple atoms arrange themselves into a layered working star. When you look at the sun, you do not see a solid surface. You see the photosphere, a layer where light last scatters before escaping. It is like the final thin veil that turns deep heat into visible glow. Below that veil, the sun grows denser, hotter, and more compressed. At the center is the core, where pressure is immense and temperatures are extreme. The core is where the sun's energy is made, quietly and steadily. Outside the core is the radiative zone, where energy moves outward very slowly. In that region, light does not travel in a straight line to the surface. It bounces and scatters, step by tiny step, in a long random walk. That outward journey can take thousands to even hundreds of thousands of years. It is a gentle reminder that the sun's output is smoothed by time. Beyond the radiative zone is the convective zone, where hot gas rises and cool gas sinks. Convection is like slow rolling movement, more like drifting than boiling. These rising and sinking motions carry energy toward the photosphere. At the photosphere, the sun's light finally streams away into space. Once light is free, it reaches Earth in a little over 8 minutes. So the light touching your skin began its last short trip minutes ago. But the energy behind that light began its story far deeper, long ago. Above the photosphere is a thin layer called the chromosphere. It can appear as a faint reddish rim during a total solar eclipse. Above that is the corona, the sun's outer atmosphere, stretching far outward. The corona is delicate and thin, yet it shapes much of space near Earth. If you picture the sun as a sphere of layered breath, you are close to the truth. The sun is not a flame in the usual sense, because it is not burning in air. It shines because of fusion, a nuclear process in the core. Fusion joins lighter nuclei into heavier ones, releasing energy. Most of the time, it turns hydrogen into helium in a chain of steps. A small amount of mass becomes energy as part of that process. This follows a simple rule. Mass and energy are two forms of the same account. The sun loses mass by shining, very slowly, second by second. A common estimate is that several million tons of mass become energy each second. That sounds large, yet compared to the sun's total mass, it is gentle and sustainable. This is why the sun can shine steadily for billions of years. Fusion also produces particles called neutrinos. Neutrinos barely interact with matter, so they leave the core almost immediately. They pass through the sun as if it were thin fog. They also pass through Earth, through oceans, rock, and you, without harm. Detecting solar neutrinos is difficult, but it has been done. Those neutrinos confirm that fusion is truly happening in the sun's core. They are like quiet receipts from the place we cannot visit. Now return to the sun's atmosphere, where surprises begin. The photosphere is around 5,500 degrees Celsius. The corona can reach temperatures of 1 to a few million degrees Celsius. So the outer atmosphere is far hotter than the visible layer below it. That result surprised scientists because it feels backward at first. It is one of the sun's most famous gentle puzzles. The leading ideas involve magnetism and waves moving energy upward. Magnetic fields can tangle, stretch, and reconnect, releasing energy as heat. Waves can carry energy through the plasma, like vibrations through a string. The details are still actively studied, and the picture keeps improving. Even without perfect answers, the pattern is clear. Magnetism matters. You can think of the sun as a magnetic star as much as a hot star. That magnetism rises from motion in the sun's interior. Moving charged particles create electric currents. Those currents generate magnetic fields that change over time. On the surface, magnetism shows up in visible features. One of the easiest to notice is the sunspot. Sunspots are darker patches, cooler than their surroundings, shaped by strong magnetic fields. They are not holes, just regions where heat flow is partly constrained. Sunspots can appear alone or in groups, drifting across the solar disk. They come and go in a rhythm called the solar cycle. The solar cycle is about 11 years from peak to peak on average. During a peak, more sunspots appear and solar activity tends to rise. During a quiet phase, sunspots are fewer and the sun looks calmer. Astronomers track the cycle by counting and measuring sunspots over time. They also watch ultraviolet and X-ray activity to understand the sun's mood. Sometimes magnetic energy releases suddenly as a solar flare. A flare is a burst of radiation across many wavelengths. Sometimes the sun also releases a cloud of plasma into space. That event is called a coronal mass ejection. A coronal mass ejection can carry magnetic fields and particles outward. When these disturbances reach Earth, they can stir space weather. Space weather is the changing environment of particles and fields around our planet. It can affect satellites, radio communication, and power systems in rare cases. But most solar activity is harmless at Earth's surface. Our atmosphere absorbs much of the most energetic radiation, and Earth's magnetic field guides many charged particles around the planet. When some particles are guided toward the poles, they can light the upper atmosphere. That is where auroras come from, a quiet glow shaped by magnetism. Later, in the space weather section, we will return to this link. For now, it is enough to know the sun reaches us in more ways than light. The sun also sends a steady outflow called the solar wind. The solar wind is a stream of charged particles flowing outward in all directions. It is usually gentle, but it is always present. It helps shape a large bubble around the solar system. That bubble is called the heliosphere. Inside the heliosphere, the sun's influence is strong compared to interstellar space. Far out, the solar wind slows as it meets the thin gas between stars. One boundary region is called the termination shock. Beyond that is the heliopause, where the solar wind yields to the interstellar medium. These are not hard walls, more like changing currents in a wide sea. The heliosphere is part shelter, part boundary marker for our neighborhood. It also affects cosmic rays, high-energy particles arriving from outside the solar system. When solar activity is higher, the heliosphere can deflect more cosmic rays. When activity is lower, more cosmic rays can reach the inner solar system. So even the sun's cycle gently changes the particle environment around Earth. If you like, hold a quiet choice in mind for a moment. Would you rather study the sun's hidden interior or its bright, hot corona? Both are real and both are filled with slow, careful discovery. Now take a calm summary, like a soft bookmark. The sun is layered with a core that fuses and an atmosphere shaped by magnetism. Its light is steady, its surface is active, and its wind extends our home outward. Next, we visit Mercury and Venus, two worlds that show how sunlight can sculpt a planet in opposite ways. If this steady pace feels good, you can tap like or save the video as a quiet bookmark. That small signal helps this kind of long, calm science keep getting made. Now, let's step onto the closest worlds, where day and year behave in unexpected ways. We begin with the two inner worlds closest to the Sun, Mercury and Venus. They sit in the same warm neighborhood, yet they tell two very different stories. First, Mercury, a small planet that lives close to sunlight. From afar, it looks like a quiet, cratered stone, like a moon with its own character. Mercury has almost no atmosphere to hold heat in place. Because of that, its temperatures swing to extremes between day and night. On the day side, ground temperatures can rise to around 430 degrees Celsius. On the night side, they can fall near -180 degrees Celsius. It is a place where sunlight feels sharp and shadow feels deep. If you like, picture a desert with no air, where heat cannot linger after sunset. And yet, Mercury holds something that sounds impossible at first. Near its poles, there are craters that never see direct sunlight. Their floors stay in permanent shadow, like pockets of night. In those cold traps, temperatures can remain low enough for water ice to persist. So there can be ice near the sun, hidden where sunlight cannot reach. It is a calm reminder that location matters less than local conditions. A steep crater rim can decide whether a patch of ground stays warm or stays cold. Some of these shadowed regions may also hold other frozen materials. The ice is not there because Mercury is cold overall. It is there because the shadows never break and cold can accumulate quietly. Now let's slow down and talk about time on Mercury. A day can mean different things depending on how you define it. One meaning is the rotation day, how long the planet takes to spin once. Mercury rotates very slowly, taking about 59 Earth days to turn once. But there is another meaning, the solar day, from one noon to the next. Because Mercury is also orbiting the Sun, that solar day stretches longer. On Mercury, a solar day lasts about 176 Earth days. That is 2 Mercury years, because Mercury orbits the Sun in about 88 days. So a single sunrise to sunrise can cover 2 trips around the Sun. Imagine standing in one place and watching the Sun crawl across the sky for months. Mercury's long days help create its intense heating and deep cooling. With little air to spread warmth, the surface follows the Sun's slow schedule. Now, Mercury is not only extreme, it is also quietly changing. Over a long time, Mercury has been shrinking a little as it cools inside. As its interior cools, the planet contracts, like a drying apple. That shrinking wrinkles the surface, creating long cliffs and ridges. These features are called scarps, and they can run for many kilometers. They are like subtle folds in rock, frozen in place. We learned much of this without sending people there. We mapped Mercury with spacecraft, reading its surface with cameras and sensors. Early glimpses came from Mariner 10, which flew by in the 1970s. Later, the Messenger spacecraft orbited Mercury and mapped it in detail. From orbit, scientists measured shape, gravity, and chemistry. Those measurements suggest Mercury has a large metal-rich core for its size. In simple terms, Mercury is more iron-heavy than you might expect. That large core affects the planet's density and its magnetic field. Yes, even this small world has a magnetic field, though weaker than Earth's. Mercury's field is another clue about its interior and its history. Pause and picture Mercury as a dense bead, sunlit on one side, ice hidden in shadow. Now let's drift outward to Venus, a planet close to Earth in size. At first glance, Venus might seem like a sister world, but its surface is one of the most hostile places we know in the solar system. Venus is wrapped in a very thick atmosphere. That atmosphere is mostly carbon dioxide, with clouds that reflect sunlight strongly. The surface pressure on Venus is about 92 times Earth's sea level pressure. It is like being deep under an ocean, but with hot air instead of water. Because the air is so thick, it holds heat and spreads it around the planet. Venus does not cool much at night. Night and day on Venus can feel surprisingly similar in temperature. Near the surface, temperatures are around 465 degrees Celsius. That heat is steady, not spiky, because the atmosphere acts like a heavy blanket. This is often described as a runaway greenhouse effect. Sunlight enters, heat builds, and thick gases trap much of that heat near the ground. Venus shows how an atmosphere can shape a world as much as rock can. It is not a warning spoken loudly, just a lesson written in physics. Now, time on Venus has its own quiet oddness. Venus rotates very slowly, even slower than Mercury. One spin of Venus takes about 243 Earth days. Venus also rotates in the opposite direction from most planets. So on Venus, the sun would rise in the west and set in the east. Even more softly strange, Venus orbits the sun in about 225 Earth days. So a Venus day, in terms of spin, is longer than a Venus year. If you stood on the surface, noon would feel like a slow change in brightness, and it would happen under a bright, thick cloud deck. Those clouds hide the surface from view in visible light. That is why radar has been so important for mapping Venus. Radar can pierce the clouds and reveal mountains, plains, and ancient lava flows. Now, while the surface turns slowly, the upper atmosphere moves quickly. Venus has something called superrotation. High winds carry the cloud tops around the planet in only a few days. So the sky can race while the ground barely turns. It is like a river of air flowing around a still stone. This fast circulation helps spread heat, supporting Venus's steady temperatures. Venus is also bright in our sky because its clouds reflect so much sunlight. It can cast faint shadows on Earth under very dark skies. That brightness is gentle to look at, but it hides intense chemistry. The clouds of Venus contain sulfuric acid droplets. They are part of a complex cycle of sunlight, gases, and reactions. Because of those clouds and pressures, Venus probes have a hard time surviving long. Several landers have returned images and data, but only for limited durations. Even so, each visit adds another calm piece to the puzzle. In recent years, Venus has also been a place of debated signals. Some observations have suggested unusual chemical traces high in the clouds. Other teams have questioned those detections or offered different explanations. This is a normal rhythm in science. Claim, test, repeat, and refine. Uncertain is not a weakness. It is a label that keeps us honest. The most trusted results are the ones that survive many careful checks. Venus is also watched from orbit by missions that study its atmosphere and weather. Japan's Akatsuki spacecraft has observed Venus's cloud motion and patterns. From those patterns, we learn about circulation, waves, and long-term change. Now, let's hold Mercury and Venus side by side for a soft comparison. Mercury is nearly airless, so its surface swings between hot and cold. Venus is air-rich, so its surface stays hot almost all the time. Mercury hides ice in permanent shadow, despite being close to the sun. Venus hides its surface under bright clouds and heavy pressure. Mercury's time is shaped by a slow spin and a fast year. Venus's time is shaped by an even slower spin and a year that passes sooner. If you like, take one quiet breath here and let the contrasts settle. Which surprised you more, ice near the sun or Venus's slow turning? From these extremes, we come home to a system with tides, eclipses, and a moon that is slowly drifting away. Now we come home to Earth and its single large moon. This pair is close enough to feel personal, yet large enough to shape time. The moon does two things at once. It stabilizes and it stirs. It helps steady Earth's tilt over long spans, and it also drives the tides. Tides are not just water rising and falling at the shore. They are a slow exchange of energy between Earth and moon. The moon's gravity pulls on Earth's oceans and even on the solid ground. It creates gentle bulges, stretched slightly along the Earth-Moon line. But those bulges are not perfectly aligned under the moon. Earth rotates, oceans have friction, and coastlines interrupt the flow. So the tidal bulges tend to lag a little behind the moon's position. That lag matters because it changes how gravity tugs back. The bulges pull on the moon, giving it a tiny forward nudge in its orbit. And as the moon gains orbital energy, it slowly moves farther away. At the same time, Earth loses a bit of rotational energy. That is the quiet trade. The moon drifts outward, and Earth's spin slows slightly. We will return later to how this gently lengthens our days over deep time. For now, just let the idea rest. Tides are a kind of cosmic break and push. Another calm fact: the moon is tidally locked to Earth. That means it rotates once for each orbit around our planet. So it always shows us nearly the same face night after night. The far side exists, but it is not the dark side. It gets sunlight too, just not at the same time we see it. This locking is common in close gravitational partnerships. Gravity tends to smooth motion into a stable rhythm. Now, the moon's slow recession is not guesswork. We can measure it directly with a method that feels almost like magic. Astronauts placed special reflectors on the moon's surface. They are arrays of corner mirrors that send light back where it came from. From Earth, scientists fire laser pulses at those reflectors. They time how long the light takes to return. Because we know the speed of light, we can calculate the distance very precisely. Those measurements show the moon is receding by a few centimeters per year today. That rate is a present-day value, not a constant across all of history. Tidal friction depends on ocean shapes and continents, which change over time. Still, the direction of change is clear. Outward drift, slow and steady. This gradual change also affects eclipses. Right now, the moon and sun appear close in size in our sky. That is why total solar eclipses are possible. But as the moon slowly moves away, its apparent size will shrink over a very long time. Far in the future, total eclipses will become rarer, then disappear. Long ago, when the moon was closer, it would have looked larger in the sky. Eclipse geometry is a slow dance of distance and perspective. Now, let's talk about months, because the moon teaches timekeeping. There are two common ways to define a lunar month. One is relative to the stars, and one is relative to the sun. The sidereal month is the moon's orbital period compared to distant stars. It is about 27.3 days. The synodic month is the cycle of phases, from new moon to new moon. That one is about 29.5 days. A gentle memory trick is that synodic syncs with the sun. The phase cycle is longer because Earth is moving around the sun at the same time, so the moon must travel a bit farther to reach the same lighting angle again. This is why calendars based on phases need careful adjustment. Now, a calm correction that often helps people. Moon phases are not Earth's shadow moving across the moon. Phases are mostly about geometry and lighting. Half the moon is always lit by the sun, just like half of Earth is lit. We see different portions of that lit half, depending on the angle. Earth's shadow only creates a lunar eclipse, and those are relatively rare. A crescent moon is simply a bright curve on a mostly unlit sphere. It is a quiet example of how perspective shapes what we think we see. Now drift down to the lunar surface itself. The moon has almost no global atmosphere. There is no weather in the way we experience it on Earth. No rain to erase tracks, no wind to soften footprints, so marks on the surface can last a very long time. Micrometeoroids and harsh sunlight slowly change the soil, grain by grain. But the change is slow, like dust settling in an empty room. Because the moon is so still, it is a record keeper. Craters remain visible for billions of years in some regions. By counting craters and comparing surfaces, scientists estimate relative ages. Older terrain tends to have more craters, like a page with more scratches. This helps build a timeline of impacts in the early solar system. One term you may hear is the heavy bombardment. It refers to a time when impacts were more frequent early in solar system history. The details are still studied, but the crater record is central evidence. The moon is also uneven inside, and that shows up in its gravity. Some regions have extra mass concentrated beneath the surface. These are called mass concentrations or mascons. Mascons can subtly tug on orbiting spacecraft, so orbits around the moon need careful planning and occasional correction. The moon looks calm, but its gravity field has quiet texture. Now let's return to Earth, and what makes our home more forgiving. Earth's atmosphere is a protective layer and a temperature manager. It spreads heat, carries water, and softens the extremes of day and night. It also shields us from many forms of harmful radiation. Most small meteoroids burn up in the atmosphere as meteors. That brief streak of light is frictional heating as they meet the air. Only some larger pieces survive to become meteorites on the ground. Earth's magnetic field adds another shield, stretching into space as the magnetosphere. It deflects many charged particles from the solar wind. Some particles spiral along magnetic field lines toward the poles. When they collide with upper atmosphere gases, they can make auroras. Those auroras are visible evidence of energy arriving from space. Later, when we talk about space weather, we will tie this to solar activity. For now, Let it be a calm thought. Earth is layered protection wrapped around life. The Earth-Moon system is a paired dance that trades energy. Tides move the moon outward and slowly soften Earth's spin. The moon keeps time in phases, while Earth keeps time in days. If you want a simple image, keep your eyes closed and picture two spheres in slow orbit. A bright blue world and a pale companion pulling and releasing like a slow breath. And if you've ever watched the moon rise, you've seen that dance from the inside. When do you usually see it? Early evening or late night? Next, we step outward to Mars, an outward-facing desert that still keeps water in quiet forms. Now we arrive at Mars, a world that feels familiar from afar, yet quietly strange up close. Mars is smaller than Earth, with lower gravity and a much thinner atmosphere. Because the air is thin, Mars cannot hold heat the way Earth does, so temperatures swing widely between day and night. The surface pressure is low enough that liquid water is not stable for long. Ice can be present, and vapor can be present, but liquid water struggles to linger. That does not mean water is absent. It means conditions are strict and fleeting. Mars also has a dusty atmosphere that shapes its weather and its light. Fine dust can hang in the air and tint the sky. It can soften shadows and give the horizon a muted butterscotch tone. Sometimes dust storms grow large and spread across much of the planet. When dust thickens, sunlight dims and the air grows hazier. Dust becomes a quiet climate actor, not just a surface layer. Mars also has seasons because its axis is tilted like Earth's. But its year is longer, so seasons last longer too. At the poles, Mars holds caps that change with the seasons. Part of those caps is water ice, and part is frozen carbon dioxide. In winter, carbon dioxide from the atmosphere can freeze onto the poles. In spring and summer, that carbon dioxide can sublimate back into gas. So the atmosphere of Mars gently breathes in and out each year. It is a seasonal pulse of air, shared between ground and sky. This breathing changes surface pressure slightly across the planet. Even on Mars, air can be dynamic, just much thinner than ours. Now, let's look at two landmarks that make Mars feel immense. One is Olympus Mons, a volcano that rises gently but reaches great height. It is a shield volcano, built by many flows of lava over long time. Mars has no active plate tectonics like Earth, at least not in the same way. On Earth, plates move and can carry volcanoes away from their magma source. On Mars, a hotspot can feed the same region for much longer. Add lower gravity, and a volcano can grow wider and taller before collapsing. So Olympus Mons becomes a gentle giant, broad as well as high. If you could stand on its slopes, it would feel like a slow incline, not a steep peak. Its size is hard to grasp because it spreads out like a massive shield. A calm scale trick is to think of it as regional, not local. It is not a mountain you hike in a day. It is a landscape you live on. Another landmark is Valles Marineris, a canyon system carved and stretched across Mars. It is not a single crack, but a complex network of troughs and chasms. One likely origin involves tectonic stretching as the crust pulled apart. Later, landslides, erosion, and perhaps ancient water helped shape the walls. Valles Marineris is so large that it can be compared to continents in length. But you do not need the exact number to feel it. Just picture a canyon system that would cross a large portion of Earth's maps. Mars carries big features because its surface has been less reshaped by oceans. Earth's water and active plates recycle and soften the crust over time. Mars preserves scars and structures for much longer spans. Now, the most persistent question people ask about Mars is about water. Mars has water, but not the kind you swim in on the surface today. We see ancient valley networks etched into old terrain. We see dried channels and delta shapes that look like rivers once flowed. We see basins that could have held lakes. These features suggest that Mars once had a different climate. Not necessarily warm everywhere all the time, but warmer and wetter at moments. The word to hold is memory. Mars remembers flowing water in its rocks and shapes. Today, water is often locked as ice. Mars has water ice at the poles, layered like pages in a book. It also has ice in the ground in many regions, not just at the poles. Landers have dug into soil and found ice just beneath the surface in some places. Orbiters using radar have mapped buried ice and layered deposits. Some radar results suggest deep ice in certain regions, protected under dust and rock. This makes Mars a world with hidden reserves, not an empty dry stone. Sometimes, scientists talk about brines, salty water that can stay liquid more easily. Salts can lower freezing points and change how water behaves. In special conditions, very salty water might briefly exist, then freeze or evaporate. These are edge cases, not stable seas. But they show that Mars still has active chemistry and seasonal change. Now let's take a soft sensory moment, because Mars also feels different. Imagine standing on Mars at dusk with a quiet, pastel horizon. The air is thin, so the sky is not a deep, rich blue like Earth's. Dust often gives it a warm, faded color in daytime, and during some sunsets, the sky near the sun can look bluish. That happens because dust scatters light in a way that favors blue near the sun's glow. It is the opposite of many Earth sunsets, where reds deepen near the horizon. Mars sunsets can feel like a gentle inversion of familiar colors. Sound is different on Mars too. Because the air is thin, sound carries less energy. It can be quieter, and it does not travel as richly as it does on Earth. Higher-pitched sounds can fade quickly, and the overall scene feels muted. Rovers have recorded sounds like wind and rover wheels, giving us a new sense of place. Even so, much of Mars is quiet, with long stretches of stillness. Now, another careful story: the search for methane and organics. Methane is a simple gas that can come from geology or from biology. On Earth, much methane is produced by living things, but not all of it. On Mars, reported methane detections have varied over time and location. Some instruments have seen hints, while others have not confirmed them globally. One reason is that methane could be local and transient, appearing and dispersing quickly. Another reason is measurement limits and differing methods. This is where science shows its calm discipline. Researchers try to replicate results with different instruments and teams. They compare lander data to orbiter data, and they look for patterns. If a signal is real, it should be consistent within known uncertainty. If it is not consistent, the story remains open, not solved. Organic molecules are another careful topic. Organic does not automatically mean alive. It means molecules built around carbon, which can form through chemistry and geology. Meteorites can deliver organics, and rocks can produce them under heat and pressure. Rovers have found organic molecules in certain rocks, which is intriguing. It suggests Mars has the ingredients and environments for complex chemistry. Whether that chemistry ever became biology is a separate question. Mars asks us to separate possible from proven and to do it gently. Now, take a small breath cue, slow and easy. Mars keeps our attention because it is close enough to study in detail. It has rich geology, a changing atmosphere, and clues to ancient climate. It is a world that holds both dust and ice, and the memory of rivers. Which image is calmer to you, Mars's dusty sky or the moon's sharp shadows? Next, we drift to the smaller worlds, rocky and icy, and often older than the planets we stand on. If you're still listening, you can leave one word in the comments. Type rocks for asteroids or ice for comets. No pressure at all. It just helps me shape the next chapters. Let's continue into the belt and beyond, where small bodies keep early solar history. Now we drift to the small worlds, the quiet archives of the solar system. These bodies are often leftovers from early formation, preserved in cold storage. They are small, but they carry big clues about what came first. Let's start with the asteroid belt between Mars and Jupiter. Many people imagine it as a crowded field of rocks, like a busy swarm. In reality, the belt is mostly empty space. Asteroids are separated by vast distances, often millions of kilometers. So collisions are not common on human timescales. Space is wide enough that most asteroids simply keep their lanes. Still, over millions of years, gravity and chance can move objects around. Some asteroids are pushed slowly by sunlight through a subtle effect called thermal recoil. Some are nudged by resonances, where orbits line up with Jupiter's pull. These slow influences can shift paths without any sudden shove. The belt contains objects of many types, from dark carbon-rich bodies to brighter rocky ones. Some are rubble piles, loosely held together by gravity. Some are more solid, like carved stone. A few are large enough to become worlds in their own right. Ceres is one of these, and it is classified as a dwarf planet. Ceres is the largest object in the asteroid belt. It is round, which tells us its gravity shaped it into a sphere. The Dawn spacecraft visited Ceres and mapped it in detail. Dawn saw bright patches linked to salts on the surface. Those salts suggest briny material from inside reached the surface at some point. Ceres also shows signs that water ice and hydrated minerals are part of its makeup. It is not a simple dry rock. It is a mixed world with a wet history. Some scientists describe it as a transition object between rock and ice. Now, not all asteroids live in the belt. Some share orbits with planets in stable gravitational spots. These stable regions are called Lagrange points, where gravity and motion balance. Jupiter has many Trojan asteroids near 2 of these points. They lead and follow Jupiter along its orbit like quiet companions. Other planets can have Trojans too, though Jupiter's are the most famous. Trojan groups show how gravity can create calm pockets of stability. Now, let's bring the small worlds closer to home. When a tiny piece of debris enters Earth's atmosphere, we call it a meteoroid. As it streaks through air and glows, we call it a meteor. If any piece survives to reach the ground, it becomes a meteorite. Most meteors are tiny, like grains of sand or small pebbles. They burn high up, far above us, and never pose a danger. That is a comforting fact to hold during a meteor shower. Meteor showers are predictable because orbits repeat. Many showers come from streams of debris left by comets. A comet travels, sheds material, and leaves a trail along its orbit. Earth crosses that trail at about the same time each year. So the shower returns each season, like a scheduled quiet show. Sometimes you see a bright meteor that flares, called a fireball. Fireballs are rarer, usually caused by larger pieces. Even then, the atmosphere does most of the work of breaking them down. Now, let's move from rocky debris to icy visitors. Comets are often described as cold archives. They formed in colder regions, where ices could survive. A comet nucleus is a small body made of ice, dust, and rocky material. When a comet stays far from the sun, it can look dark and inactive. As it approaches sunlight, its ices begin to sublimate. Sublimate means they go from solid directly to gas. That gas carries dust with it, forming a fuzzy cloud around the nucleus. This cloud is called the coma. As the comet continues, the coma can grow large and luminous. Then tails can form, stretching away into space. Comets can have 2 main kinds of tails. One is the dust tail, made of fine particles pushed by sunlight. The dust tail often curves gently, following the comet's path. The other is the ion tail, made of charged gas. The ion tail is shaped by the solar wind, a stream of particles from the sun. Because of that, the ion tail tends to point away from the sun. Even if the comet is moving in another direction, that tail aligns with the wind. So a comet's tails are like windsocks in space. They show sunlight pressure and solar wind direction at the same time. Later, when we talk about space weather, we will revisit that solar wind. For now, just keep the image. Two tails, two forces, one quiet traveler. We have visited comets up close with spacecraft. The Rosetta mission orbited a comet and watched it change as it warmed. It showed that comet surfaces can be rugged with cliffs and jets. Jets are localized outgassing streams, like small vents releasing vapor and dust. Even these jets are driven by sunlight, not by fire, just by warming. Now step farther out, beyond Neptune, into the Kuiper Belt. The Kuiper Belt is a region of many icy bodies on slow, distant orbits. It is like a wider, colder cousin of the asteroid belt. Pluto is part of this broader population. When Pluto was discovered, it seemed like a lone ninth planet. Now we know it is one of many similar bodies in that far region. The light out there is faint, and the sun is a small bright point. Years are long and seasons can last decades. Many Kuiper Belt objects have eccentric or tilted orbits. Some are in resonant orbits, meaning their periods keep a stable ratio with Neptune. Resonance is a repeating gravitational rhythm that can protect an orbit from chaos. Neptune's gravity helps sculpt the Kuiper Belt structure over time. Pluto itself is in a resonance with Neptune that keeps them safely separated. These are quiet examples of how gravity can organize a distant crowd. Beyond the Kuiper Belt is an even more distant idea, the Oort cloud. The Oort cloud is not directly imaged. It is a hypothesis supported by the behavior of long-period comets. Some comets arrive from far outside the planetary region on very long-stretched orbits. Their paths suggest a reservoir of icy bodies at enormous distances from the Sun. So the Oort cloud is inferred from orbits not seen with cameras. This is another example of science using indirect evidence carefully. As more comets are tracked and their paths refined, models are updated. The map improves as the data grows without forcing certainty too soon. Now, one more topic that small worlds bring into focus: impacts. Impacts are rare in a single human lifetime, but important across history. Small impacts happen often, but most never reach the ground in dangerous form. Large impacts are far less frequent, yet they can reshape climates and surfaces. Craters act like clocks in the solar system. On bodies with little erosion like the Moon, craters can remain for eons. On Earth, weather, oceans, and plate tectonics erase many old craters. So Earth's impact record is incomplete, even though impacts happened here too. Studying small bodies helps us understand both risk and history. It also shows how material was delivered and mixed in the early solar system. Missions have visited asteroids and returned samples to Earth. OSIRISRE-X brought material from the asteroid Bennu. Hayabusa missions returned samples from asteroids as well. These samples are like time capsules you can hold in a lab. They carry minerals, organics, and clues from the solar system's youth. So small worlds are not side notes. They are the memory of the beginning, scattered in slow orbit. If you could visit one small world, would you prefer a rocky asteroid or a bright comet? From small archives, we move to the giants whose gravity shapes the entire solar system. Now we reach the giants, Jupiter and Saturn, where gravity shapes everything nearby. They are mostly hydrogen and helium, more like small stars that never ignited. Their clouds are not a thin skin, but deep layers with changing chemistry. Jupiter is the largest planet in our solar system, and it still holds internal warmth. It gives off more heat than it receives from the distant sun. That extra heat comes from slow contraction and leftover energy from formation. Imagine a huge sphere very slowly settling, releasing warmth as it tightens. Jupiter also spins fast, completing a rotation in about 10 hours. Fast rotation makes it slightly flattened, like a softly squashed ball. That spin also helps organize its clouds into bands and zones. The bands are streams of wind, flowing in opposite directions side by side. Some winds are faster than any hurricane on Earth, but they are spread wide and steady. If you picture a striped planet breathing and turning, you have the right mood. One of Jupiter's best-known features is the Great Red Spot. It is a long-lived storm, observed for centuries, changing slowly over time. Its size and its color have both shifted over decades. Sometimes it looks deeper red, sometimes more muted, like a stain in moving clouds. Storms on Jupiter can last because there is no solid surface to break them up. They feed on temperature contrasts and the planet's rapid spin. Around the red spot, smaller storms appear, merge, and fade like drifting eddies. If your mind wants a calm anchor, return to the slow swirl of that oval cloud. Now, beneath the clouds, Jupiter's interior becomes stranger. Pressure rises until hydrogen behaves in unusual ways. Deeper down, hydrogen can become metallic, able to conduct electricity well. That conductive layer helps generate Jupiter's powerful magnetic field. Jupiter's magnetosphere is enormous, a vast magnetic bubble around the planet. It traps charged particles and guides them along field lines. This creates intense radiation belts, like a harsh weather zone for spacecraft. Exploring Jupiter means designing electronics and shielding with great care. Some regions are so energetic that spacecraft limit time spent there. Jupiter also has auroras persistent and bright in ultraviolet and infrared light. They are driven by both the solar wind and Jupiter's own fast rotation. In a quiet way, Jupiter makes its own space weather. Now, let's step closer to the moons, which form a miniature system. Jupiter has many moons, but 4 are especially famous. They are Io, Europa, Ganymede, and Callisto. They were first seen through a telescope by Galileo long ago. These 4 moons orbit in an orderly pattern, like a small solar system. Their gravity interactions keep their orbits slightly stretched and timed together. That stretching becomes internal flexing, and flexing becomes heat. Io is the clearest example of tidal heating in action. Io is the most volcanically active body we know. Its surface is reshaped by lava and sulfur-rich deposits. Some volcanoes on Io erupt so powerfully they send material far above the surface. But the cause is not an internal furnace alone. It is Jupiter's gravity, kneading Io like a slow, steady hand. Each orbit flexes Io's interior, generating frictional heat, so Io glows with geology powered by orbital motion. Next is Europa, quieter on the surface and more mysterious underneath. Europa is covered in ice, crisscrossed by long cracks and ridges. The surface looks young in places with fewer impact scars. Multiple lines of evidence suggest a global ocean beneath the ice. That evidence comes from Europa's shape, gravity effects, and magnetic signatures. In simple terms, something conductive and moving may be hidden below. A salty ocean fits that picture, protected from vacuum by ice. If you picture a dark ocean under a pale shell, you are close to Europa's appeal. Europa is one of the most promising places to study ocean worlds. Now to Ganymede, the largest moon in the solar system. Ganymede is even larger than the planet Mercury, though far less massive. It has a mix of bright and dark terrain, like old and new layers side by side. Ganymede also has its own magnetic field, which is rare for a moon. That means it can form a small magnetosphere inside Jupiter's larger one. It is like a bubble within a bubble, nested and interacting. Callisto, the 4th large moon, is more heavily cratered and ancient-looking. It appears less internally active than Europa or Io. Callisto reminds us that not every moon is stirred into change. Together, these moons show how gravity can create many outcomes from similar ingredients. Now let's glide outward to Saturn, the second giant, soft in color and famous for rings. Saturn is less dense than many people expect. Its average density is lower than water, though floating is only a thought experiment. There is no bathtub large enough, and the physics would not cooperate. Still, the comparison helps your intuition about how light Saturn really is. Saturn also has bands and storms, but they are often subtler than Jupiter's. Its atmosphere can show pale yellows and gentle tans under the haze. Saturn's rotation is also fast, and it shares that slightly flattened shape. Now, the rings. Saturn's rings are broad in diameter, but surprisingly thin in thickness. They are made mostly of water ice particles, from dust-sized grains to boulder-sized chunks. From afar, they look like a smooth disk, but up close, they are countless small orbits. The rings reflect sunlight well, which is why they look bright. Their brightness changes with our viewing angle from Earth. When we see the rings more edge-on, they can seem to fade. When we see them more open, they look wide and luminous. This is a seasonal effect from our perspective as Saturn moves along its path. If you want a restful image, picture the rings as a quiet record player turning slowly. Now, Saturn's moons add their own calm surprises. Titan is Saturn's largest moon, wrapped in a thick atmosphere. Titan's air is mostly nitrogen, like Earth's, but colder and richer in haze. That haze hides the surface in visible light, creating a soft orange veil. Titan has methane clouds, and methane can fall like rain there. On Titan's surface are lakes and seas of liquid hydrocarbons, like methane and ethane. So Titan has shorelines, but of chemistry unfamiliar to our oceans. It is a world where rivers can flow, just made of different liquids. Titan's atmosphere and chemistry make it a natural laboratory for complex molecules. Now to Enceladus, much smaller, but remarkably active. Enceladus is an icy moon with bright, reflective surface regions. Near its south pole, jets of material spray out into space. These plumes were observed by the Cassini spacecraft as it flew through the region. The plumes contain water vapor, ice grains, and hints of salts and organics. Those ingredients suggest liquid water beneath the ice, kept warm by tidal heating. It is another ocean world, but one that leaks samples into space. That makes Enceladus especially inviting for future study. When we later talk about exoplanet atmospheres, remember this moment. We often learn by reading faint signals, whether from starlight or from plume particles. Now, take a slow reset as if you are recentering in a dark room. A Jupiter, fast spin, deep bands, a long-lived storm, and a huge magnetic bubble. Its moons range from volcanic fire to hidden oceans to magnetic mini-worlds. Saturn, lighter than you expect, wrapped in thin rings of ice. Its moons offer haze-thick skies and icy plumes from below. Imagine bands, rings, and moons as separate laboratories, all turning in quiet rhythm. If you drifted for a moment, you have not missed the thread. The thread is gravity shaping heat, motion shaping weather, and distance shaping calm. Now we move outward to the ice giants, where sunlight is faint and seasons can last decades. Which feels more soothing to imagine, Saturn's rings or Titan's hazy sky? Now we move outward, where sunlight is faint and the planets feel more like quiet lanterns. Uranus and Neptune are called the ice giants. They are not made mostly of ice cubes, but of materials like water, ammonia, and methane mixed under pressure. Their outer layers are gas, and their deeper interiors are warm, dense fluids. First, Uranus, the planet that seems to roll around the sun on its side. Uranus has an extreme axial tilt, close to 90 degrees. That means its poles take turns facing the sun for long stretches. Its seasons are unlike Earth's seasons. For part of its year, one hemisphere can be in continuous daylight, and the other hemisphere can be in long, continuous night. Because Uranus is far from the sun, its year is long, so those unusual seasons last for many Earth years at a time. Sunlight geometry changes slowly, like a dim lamp rotating around a room. If you imagine a planet lit from the side, you are close to Uranus's posture. Uranus also has a magnetic field that is unusual. It is tilted relative to its rotation axis and offset from the planet's center, so its magnetosphere can be complex and lopsided. As Uranus spins, the magnetic environment wobbles through space. It is like a lantern with the flame set off center. turning in the dark. That creates changing particle pathways and a shifting auroral setup. Uranus can produce auroras, though they are not as famous as Jupiter's. Now, Uranus can look subtle in visible light. It often appears as a smooth blue-green disk with few obvious features. That calm look can be misleading. Distant planets can appear quiet while still being dynamic. With better instruments, we see hazes, bands, and occasional storms. Some storms have been detected as bright clouds in the upper atmosphere. Methane in the atmosphere absorbs red light and leaves a cooler blue-green tone. High, thin hazes can soften contrasts, making features harder to see. Uranus also has rings, though they are faint and narrow compared to Saturn's. They are dark and thin, and were discovered through careful observations. Uranus has many small moons as well, some shepherding ring structures. Together, rings and moons form a delicate system in low sunlight. Now we drift a little farther to Neptune, deeper blue and more visibly active. Neptune is even farther from the Sun than Uranus. Yet, Neptune has very fast winds, among the fastest in the solar system. That seems surprising, because sunlight out there is weak. One key reason is that Neptune has notable internal heat. It radiates more energy than it receives from the Sun. That internal heat helps drive weather and winds from within. So Neptune is powered partly by its own warm interior. Neptune's blue color is also linked to methane absorption and atmospheric scattering. Its clouds can appear as bright white streaks and spots in telescope images. Neptune can host large storms that appear and fade over time. A historical example is the Great Dark Spot seen by Voyager 2. It was a large dark storm system, like a cousin to Jupiter's famous oval. Later observations showed that particular spot disappeared. New dark spots have been seen since, forming and fading as Neptune's weather shifts. So Neptune's storms are real, but not necessarily permanent. Neptune's winds can be extreme, yet the planet remains a quiet dot from Earth. That contrast can feel soothing in its own way. At great distance, even violence becomes silence. Now we enter a part of the story where we separate observation from model. Deep inside Uranus and Neptune, pressures are enormous. At those pressures, familiar materials behave in unfamiliar ways. Scientists use theory and laboratory experiments to explore these conditions. They compress materials and heat them, trying to mimic deep planetary interiors. One idea that often captures attention is diamond rain. This is not observed directly on either planet. It is a model-based possibility suggested by high-pressure chemistry. In some models, methane under great pressure can break apart. Carbon could then form solid phases, potentially diamond-like structures. Heavier carbon phases could sink, releasing heat as they fall. This remains an active area of research and modeling. The calm takeaway is that deep planets can have deep chemistry, tested step by step. Science labels the difference between what we see and what we infer. That distinction keeps the story sturdy and honest. Now, Neptune's moon Triton adds another quiet surprise. Triton orbits Neptune in the opposite direction of Neptune's rotation. A retrograde orbit like that suggests Triton was captured. Capture is difficult, but the solar system has had long time to arrange rare events. Triton is cold, bright, and covered with ices. Voyager 2 saw geyser-like plumes on Triton's surface. These plumes likely involve nitrogen ice warmed by seasonal sunlight. When sunlight warms nitrogen frost, gas can build and escape through vents. The result is a gentle spray, leaving dark streaks on bright terrain. Triton shows that even far out, surfaces can still be active. It is a captured world that became part of Neptune's family, and it hints at how many kinds of moons might exist around other planets. In a moment, we will leave the solar system and meet planets around other stars. Before we go, take a soft reset at the edge of our planetary family. Faint sunlight, long years, and internal heat sources shape these distant worlds. Uranus, sideways seasons, and a tilted off-center magnetic field. Neptune, deep blue winds and storms that come and go. Moons and rings add fine structure, like quiet handwriting around each planet. If you want a calming image, imagine distant blue light and slow-moving cloud layers. Now the universe gets crowded, with thousands of exoplanets waiting beyond our sun. Do you prefer the idea of a long season or a short season, and which feels calmer? With the solar system in mind, we can compare it to the thousands of planetary systems beyond it. If these steady fact chapters help you settle, you can subscribe. Many listeners use one video as a nightly routine, and subscribing makes the next calm journey easy to find. Now we step into other solar systems, where planets can be stranger than fiction, yet still real. Now we leave our solar system and step into a crowded sky of other worlds. These are exoplanets, planets that orbit stars beyond the sun. We do not see most of them as tiny disks, the way we see Jupiter through a telescope. Instead, we notice them through small, repeated signals in starlight. That is part of the charm. Huge discoveries made from gentle hints. Over the past few decades, exoplanets moved from rumor to routine science. Today, thousands are confirmed, and many more candidates wait for follow-up. Even with that large catalog, we still find the easiest ones first. This is called detection bias, and it is a helpful filter to remember. Our methods prefer big planets, close to their stars, moving on short, regular orbits. So the early exoplanet zoo looked extreme, and then it slowly filled in. One surprise was the hot Jupiter. A hot Jupiter is a gas giant orbiting very close to its star. In our solar system, gas giants live far out, where it is colder. So finding a Jupiter-like world hugging its star was unexpected. Hot Jupiters taught us that planets can migrate after they form. Migration is a slow reshaping of orbits by disks of gas or by gravitational nudges. It is not a sudden jump, more like a patient drift over a long time. Some hot Jupiters likely formed farther out and moved inward. Others may have had their paths altered by close encounters with other planets. This matters because a moving giant can reshape smaller worlds nearby. It can scatter rocky planets or feed them inward or clear a region out. So one planet's history can quietly rewrite an entire system. Another surprise was how common medium-sized planets appear to be. Many stars host worlds larger than Earth, but smaller than Neptune. These are often called super-Earths or mini-Neptunes. The names describe size, not necessarily surface conditions. A super-Earth might be rocky, or it might have a thick atmosphere. A mini-Neptune might be a water-rich world, or a small gas planet with haze. Our solar system has no perfect match for these common sizes. That tells us our local lineup is not the universal template. Some of these planets may have deep oceans under high-pressure atmospheres. Some may have hot, dense air and no solid surface you could stand on. Some may be mostly rock with a thin envelope of gas like a soft coat. To find them, we often use the transit method. A transit happens when a planet passes in front of its star from our viewpoint. The star's light dips by a tiny amount, then returns to normal. Timing those dips reveals the planet's orbital period. The depth of the dip hints at the planet's size compared to the star. This is like noticing a small moth cross a porch light far away. The same star can host multiple planets, each with its own rhythm of dimming. Some systems pack several planets closer than Mercury is to the Sun. They can orbit like a string of quiet beads, each on its own schedule. Sometimes a planet's gravity nudges another planet's transit time by seconds or minutes. Those tiny timing shifts can reveal hidden companions we do not directly see. We also find some planets by microlensing, when gravity briefly magnifies a distant star. Another method tracks a star's slow wobble. As a planet orbits, it tugs the star back and forth slightly. We detect that motion through tiny shifts in the star spectrum. That gives a measure related to the planet's mass. When we combine mass and size, we can estimate density. Density is a calm clue. Airy, watery, rocky, or metal-rich. Now let's visit an even stranger neighborhood, ultra-short period planets. These worlds orbit so close that their years last only hours or a few days. Starlight there is intense, and the surface can be heated to extreme temperatures. Some are called lava worlds because rock may melt or soften on the day side. On a very close orbit, tides can lock the planet's rotation. One hemisphere faces the star in permanent day. The other hemisphere faces away in permanent night. Between them is a twilight band, sometimes called the terminator region. It can be a place of strong winds, as air flows from hot to cold. If the planet has an atmosphere, it may carry heat toward the night side. Clouds might gather near that boundary, where temperatures cross a threshold. On some close-in rocky planets, material may even escape into space. Intense heating can lift atoms or dust from the surface into a thin stream. In a few cases, we see hints of dusty tails trailing a planet like a comet. Picture a slow ribbon of particles, backlit by the star, fading into darkness. These worlds are harsh, yet the physics is graceful and consistent. Farther out, we also find planets on long orbits, colder and quieter. Some are gas giants with years like slow clocks, taking decades to circle once. Some are small and icy, receiving only a dim fraction of their star's warmth. The variety is wide, and it keeps widening as our searches improve. Now, beyond size and orbit, we want to know what these planets are like. The hardest question is also the most human. What is the atmosphere made of? One way is to read starlight during a transit. As the planet crosses the star, a thin ring of light filters through its air. That filtered light can carry faint, spectral fingerprints of gases. These measurements are difficult, and they often depend on careful models. Still, they let us infer hints of water vapor, carbon-bearing molecules, and hazes. Another method looks at the planet's own glow in infrared light. When a planet passes behind its star, the combined light drops slightly. That drop can reveal the planet's thermal emission, like a warm ember. By watching brightness through an orbit, we can trace a phase curve. A phase curve is a gentle map of how light changes with planetary day and night. It can hint at where the hottest region sits and how winds move heat. These are not photographs of continents. They are careful deductions from small changes in light. That is why exoplanet science values repeated observations and cross-checks. Now, many people ask about the habitable zone. The habitable zone is a useful idea, the range where temperatures could allow liquid water. But it is not a guarantee of oceans or life. Atmospheres can warm or cool a planet dramatically. Clouds can reflect starlight and lower temperatures. Greenhouse gases can trap heat and raise temperatures. Geology can cycle gases over time, reshaping climate from within. And the star itself matters as much as the planet. Small, cool red dwarf stars are common, and their habitable zones sit very close in. Close-in orbits raise the chance of tidal locking and strong stellar influence. Some red dwarfs flare often, sending bursts of energetic radiation. Yet red dwarfs can also live for a very long time, offering stable light over ages. So there are trade-offs, not simple labels. The calm truth is that habitability is a full system story, not a single distance. If you like, pause and choose a world to imagine for a moment. A cool ocean world, a cloudy twilight world, or a quiet ice world. There is no right answer, just a gentle place for your mind to rest. However we picture them, we find these planets by timing, dimming, and subtle motion. And to understand those worlds, we need to understand their stars. Next, we move from planets to the suns that shape them with color, size, and lifespan. Now we focus on stars themselves, the furnaces and clocks of the universe. A star is not just a light in the sky. It is a balance between gravity pulling inward and hot pressure pushing outward. That balance can last for millions or billions of years. One of the simplest star clues is color. A star's color is linked to its surface temperature. Try to think of temperature as a smooth gradient, not a sharp label. Blue-white stars have hotter surfaces. Yellow stars like the sun sit in the middle of the range. Orange and red stars have cooler surfaces. Cooler does not mean cold like ice. It still means thousands of degrees. But within star physics, that difference matters a lot. Hotter surfaces glow more strongly in shorter wavelengths. Cooler surfaces glow more in longer wavelengths. This is why color can be a thermometer if we measure it carefully. Our eyes can be fooled, though. Star colors are often subtle to human vision, especially in a bright sky. Camera sensors, filters, and image processing can exaggerate color differences. So astronomers rely on measured spectra and calibrated photometry. Still, the overall rule holds: bluer is hotter, redder is cooler. Another gentle surprise is what kinds of stars are most common. Most stars in the Milky Way are red dwarfs. A red dwarf is a small, cool star with low mass. Because it has less mass, its core pressure is lower. And because of that, it burns fuel more slowly. Slow fuel use means a very long life. Many red dwarfs can shine steadily for times far longer than the sun's total lifetime. They are quiet lanterns that can outlast many cosmic events. This matters for planets because a long-lived star offers a long window of light. But there is a trade-off that stays important. The habitable zone around a red dwarf is close-in because the star is dimmer. Close-in planets can become tidally locked more easily. And many red dwarfs have active periods, especially when they are young. They can produce flares that send bursts of energetic radiation. A planet close to a flaring star may need strong protection to hold an atmosphere. Later, when we discuss radiation and space weather, we will connect these ideas. For now, hold a calm balance, long lifetimes, but sometimes lively activity. Now, move to the other end of the stellar spectrum. Massive stars lie fast because their gravity squeezes their cores harder. Higher pressure raises temperature and speeds up fusion reactions. So massive stars spend fuel quickly and burn brighter while they do it. A massive star might live only millions of years, not billions. It is a brief, intense life by cosmic standards. As stars age, their fusion changes in stages. For a long time, many stars fuse hydrogen into helium in their cores. That is the quiet main phase of most stellar lives. When hydrogen runs low in the core, the balance shifts. The core contracts and heats, and the outer layers can expand. The star can become a giant, swelling in size while changing its internal structure. In more massive stars, fusion can progress to heavier elements. Helium can fuse into carbon and oxygen under the right conditions. Later stages can build elements like neon, magnesium, silicon, and sulfur. These stages are like nested shells of burning, each with its own temperature needs. The process is not rapid from our perspective, but it accelerates near the end. The most stable stopping point is iron. Fusing iron does not release energy the way lighter fusion does. So when an iron core forms in a very massive star, the story tightens. That is where dramatic endings can begin, but we will save the details for the next section. For now, keep the gentle idea. Stars are the slow craft of element making. Many atoms in your body were formed in earlier stars. Carbon, oxygen, nitrogen, and iron are part of that long stellar history. Some of the heaviest elements are made in explosive events, where conditions are extreme. So the periodic table is partly a record of stellar lives and deaths. Even before an explosion, massive stars lose mass through stellar winds. A stellar wind is an outflow of gas from a star's outer layers. In supergiants, these winds can be strong and persistent. They shape the environment around the star, forming shells and bubbles. That lost mass can affect how the star ends and what it leaves behind. Now let's return to a calmer kind of star behavior: variability. Not all stars shine at a perfectly constant brightness. Some brighten and dim in regular, predictable patterns. These are variable stars, and their changes can be very useful. One important group is Cepheid variable stars. Cephides expand and contract in a steady rhythm, like slow breathing. That breathing changes their brightness in a repeatable way. Cephides have a link between their pulsation period and their true brightness. So if we measure the period, we can infer luminosity. And if we compare luminosity to apparent brightness, we infer distance. This is one of the reasons astronomers can map galaxies and clusters. Stable patterns become measuring tools, which is a very calm kind of power. Variable stars are not flickering randomly. They are following physical modes, driven by pressure and opacity changes inside. Think of it like a musical instrument with a resonant note. The star rings in a slow, thermal way. Now, stars also have beginnings, and those beginnings happen in dark places. Star nurseries form inside cold molecular clouds. These clouds are wide regions of gas and dust. They can be so dusty that they block visible starlight behind them. From Earth, they can look like dark patches against a bright background. Inside, gravity slowly gathers denser clumps. As a clump collapses, it warms, forming a protostar. A protostar is not fully a star yet, but it is on the way. Often, a disk forms around the young object, made of leftover gas and dust. Those disks are where planets can begin to assemble. This is how the story loops. Stars form and planets form in their company. Dust that blocks visible light can glow in infrared, so infrared telescopes can reveal warm nursery regions hidden from our eyes. In those nurseries, you can find jets, outflows, and pockets of new light. But the overall scene is slow and patient, like fog condensing into drops. If you want a gentle image, picture a quiet cradle of gas slowly tightening. Now take a small reset, like a bookmark for your mind. Stars are temperature, gravity, and time, all read through light. Color hints at surface heat, mass hints at lifetime, and spectra reveal chemistry. Most stars are red dwarfs, long-lived and common. Some stars grow into giants and make heavier elements in layered fusion, and some stars pulse with steady rhythms that help us measure distance. If you could watch one star phase, would you choose birth in a nebula or calm main sequence life? Next, we compress matter to extremes, where stars leave behind dense remnants. Now, we move from steady starlight to the densest objects known, where gravity changes how time feels. Now we move into the densest stellar remnants, where gravity becomes a strong sculptor. These are not monsters in the dark. They are distant laboratories, showing what matter does at extreme pressure. A star's end depends mostly on its mass and how it spends its fuel. Let's begin with the white dwarf, the quiet ember left by many sun-like stars. When a medium-sized star runs out of core fuel, it cannot support itself the same way. Its outer layers drift outward, and the core remains behind. That core becomes a white dwarf, about Earth-sized, but far more massive than Earth. A white dwarf no longer fuses hydrogen in its center. It shines mainly from stored heat, cooling slowly over a very long time. What holds it up is not fusion pressure, but a quantum effect. This support is called electron degeneracy pressure. It comes from the rule that electrons resist being squeezed into the same state. You do not need the math to feel it. Think of it as matter reaching a firm, quiet limit to compression. But there is a maximum mass where this support can no longer hold. If a white dwarf becomes too massive, collapse can continue. This mass limit is a key idea in stellar endings. In some binary systems, a white dwarf can gain matter from a companion star. If it approaches the limit, it can ignite runaway fusion under high pressure. That event can produce a Type 1a supernova. These explosions reach similar peak brightness in many cases. That is why they are used as distance markers across galaxies. So a small, dense remnant can become a measuring tool for the whole universe. Now we go denser still to neutron stars. Neutron stars form when a more massive star collapses after its life of fusion. The core compresses beyond white dwarf support, protons and electrons combine into neutrons, creating neutron-rich matter. The result is a star-sized mass packed into a city-sized sphere. A neutron star can be only about 20 kilometers across, yet it can contain more mass than the Sun. This is hard to picture, so keep it gentle. It is simply very, very dense. Gravity near the surface is intense, and the crust is likely an exotic solid. Neutron stars can rotate quickly. Some spin many times per second, steady and precise. When their magnetic poles sweep past our line of sight, we detect pulses of radio waves. These are pulsars like rotating lighthouses in space. Their pulses can be so regular that they rival the stability of atomic clocks. Pulsars help test physics, map interstellar gas, and even keep time. Some neutron stars have magnetic fields that are especially strong. These are called magnetars. A magnetar's field can influence nearby plasma and reshape its surroundings. It can power bursts of high-energy radiation when the crust shifts. Even so, from far away, it is still a small point of light in a large sky. Now we step to black holes, the most famous remnants of all. A black hole is a region where gravity becomes so strong that escape is impossible. The boundary of that region is called the event horizon. Inside, the escape speed exceeds the speed of light. That is why light cannot travel outward from within that boundary. But it helps to remember something calming. From far away, a black hole's gravity behaves like any other mass. If the Sun were replaced by a black hole of the same mass, Earth's orbit would stay nearly the same. The difference is not the pull at a distance. The difference is what happens very close in. Black holes do not act like vacuum cleaners pulling everything in. Objects must come close, often by losing orbital energy, to fall inward. We rarely see black holes directly because the hole itself emits no light. What we often see is the environment around them. Gas falling toward a black hole can form an accretion disk. As gas spirals inward, it rubs and heats, glowing brightly in X-rays and other light. So the disk can shine while the black hole remains dark. Some black holes also launch jets, narrow streams of particles along their poles. Those jets are linked to magnetic fields and spinning material near the hole. Again, the hole is not glowing by itself. It is the motion and heating of nearby matter that makes the light. Now let's connect these remnants to what we see across the universe. Strong gravity can bend the path of light. This is called gravitational lensing. A massive object between us and a distant source can curve spacetime. Light then follows curved paths, and the background object can appear magnified. Sometimes we see arcs, rings, or multiple images of the same galaxy. Lensing is not a trick of the eye. It is geometry in curved spacetime. Later, we will use lensing again when we talk about dark matter and cosmic structure. Lensing is one of the ways we map mass we cannot see directly. Gravity also affects time in principle. Closer to strong gravity, time runs a bit differently compared to far away. This is called gravitational time dilation. In everyday life, the effect is tiny, but measurable with precise clocks. Near a neutron star or black hole, the effect can be stronger. Still, what matters depends on distance and on where you are observing from. We keep it practical by remembering the scale of separation. Now, there is another kind of message that comes from these dense objects. It is not light, but ripples in spacetime itself. These are gravitational waves. Gravitational waves are produced when massive objects accelerate asymmetrically. One strong source is a merger of two black holes or two neutron stars. As they spiral together, they stir spacetime like a slow, tightening whirl. Detectors on Earth can measure these waves as tiny changes in length. They use lasers to compare distances along long arms with incredible precision. This is what observatories like LIGO, Virgo, and Cagra do. They turned gravity into a sense we can listen with. In some events, we have more than one messenger. A neutron star merger can produce gravitational waves and light, and sometimes neutrinos in related processes. This is called multi-messenger astronomy. It lets us cross-check the story the way we cross-check spectra and distances. It is new in human history, a fresh channel of information. But the universe has always been sending these waves. We simply learned how to notice them. Now, take a calm reset because these topics can sound heavy. White dwarfs, neutron stars, and black holes are far away and not threats to our daily life. They are evidence that nature follows rules even at extremes. They show what pressure, rotation, and gravity can do to matter. If you want a soothing image, picture gravity as a smooth curve in space, not a sudden edge. A curve that guides motion quietly, whether around a planet or around a remnant, which feels most interesting in a calm way. Pulsars, lensing, or waves. Next, we zoom out to galaxies, their shapes, their slow collisions, and the unseen matter that holds them together. Now we zoom out from single stars and remnants to whole galaxies. A galaxy is a vast system of stars, gas, dust, and dark matter held together by gravity. It is a long-lived city of light, drifting through a darker sea. Galaxies come in a few broad shapes, each with its own calm logic. One common type is the spiral galaxy. Spirals have flat disks with arms that curve outward like gentle pinwheels. Those arms are not rigid structures made of the same stars forever. They are more like density waves, regions where material bunches up as it orbits. When gas is compressed in those regions, it can form new stars more easily. So spiral arms often host star formation in bright, young clusters. The disk can be dusty, and that dust can hide parts of the galaxy in visible light. Above and below the disk is a more diffuse halo with older stars and globular clusters. Another major type is the elliptical galaxy. Ellipticals look smoother and more rounded, like softly glowing ovals. Many have older star populations and less cold gas for new star formation. They can form through mergers, where disks are disrupted and stirred into a rounder shape. Not every elliptical has the same story, but mergers are a common path. Ellipticals can also be very massive, with huge numbers of stars packed into a bright core. A third category is the irregular galaxy. Irregulars do not have a clean disk or a smooth oval shape. They can look messy, patchy, and lively. Often their shapes are influenced by interactions, tides, or ongoing star birth. In some irregulars, star formation can be intense and clumpy, like bright knots in fog. So when you picture a galaxy, you might see a spiral, an oval, or something more chaotic. Now, let's visit our home galaxy with a little more detail. The Milky Way is a barred spiral galaxy. That means it has a central bar of stars with spiral arms extending from that bar. We cannot take a full face-on photo from inside it, so we infer its structure from star motions, gas mapping, and careful modeling. We measure how stars move, how gas clouds drift, and how dust blocks light. We use radio and infrared observations to see through dust that hides the disk. In visible light, many inner regions are veiled by thick dust lanes. In infrared, more of the galaxy's heart is revealed. At the center of the Milky Way is a supermassive black hole. It is called Sagittarius A star, and it is quiet most of the time. It is not constantly feeding or blazing like an active galaxy core. Most of the time, it sits with low activity, a calm anchor of mass. We know it is there because we can track stars orbiting an unseen center. Those stars move quickly on tight paths, as if circling something very massive. That is one of the cleanest ways to infer a central black hole. Now, galaxies do not live alone. They grow by interacting, merging, and sometimes absorbing smaller neighbors. Gravity creates tides between galaxies, stretching them like slow taffy. When a small galaxy is pulled apart, its stars can form long streams. These stellar streams can wrap around the larger galaxy like faint ribbons. They are evidence of past mergers, written as dim arcs across the sky. Mergers can also trigger bursts of star formation. When galaxies collide, gas clouds can be compressed and disturbed. That compression can cause new stars to form in large waves. So some galaxies shine brightly in infrared because of intense star birth. Other mergers can funnel gas toward the center, feeding a central black hole. That can light up an active galactic nucleus, bright across many wavelengths. But not every collision makes fireworks. Many mergers are slow, drawn-out blends over hundreds of millions of years. Two spiral galaxies can pass, stretch, and return like dancers meeting again and again. One famous neighbor in our own group is the Andromeda Galaxy. Andromeda is a large spiral not far away on cosmic scales. It and the Milky Way are on a very long-term approach. Over billions of years, they are expected to interact and eventually merge. The exact timing and details are still refined, so think of it as a distant future drift. It is not a near-term event, just part of the galaxy life cycle. Now we come to the invisible scaffolding that holds galaxies in place. This idea is called dark matter. Dark matter is not seen directly in light, but its gravity is measured. One clue comes from galaxy rotation curves. In a simple picture, stars farther out should orbit more slowly if only visible mass mattered. But many galaxies show outer stars moving faster than expected. These speeds stay high even where visible light grows thin. This suggests extra mass beyond what we see. That extra mass behaves like an extended halo around the galaxy. Another clue comes from gravitational lensing. When a cluster of galaxies bends light, we can map how much mass is present. Sometimes the lensing mass does not match where the visible matter is concentrated. This is especially clear in some colliding galaxy clusters. Lensing lets us trace mass whether it glows or not. So we see dark matter by its gravitational influence, not by its substance directly. We do not yet know its particle nature with certainty, but the gravitational evidence across many systems is strong and consistent. Now, zoom out further beyond individual galaxies and clusters. On the largest scales, matter is arranged in a cosmic web. Galaxies cluster along filaments, like beads on long threads. Between filaments are vast regions called voids. Voids are not truly empty. They still contain gas, dark matter, and some galaxies. They are simply far less dense than the filaments and clusters. If you could see the universe as a three-dimensional map of density, it would look foamy. Dense walls and threads with bubbles of lower density between them. This web is traced not only by galaxies, but also by thin gas between them. Some of that gas is detected through faint absorption in distant quasar light. So the web is both luminous and hidden, depending on how you look. The cosmic web is a structure on top of structure. Stars form in galaxies, galaxies gather in groups, groups form clusters, clusters follow filaments, and the filaments span millions of light years, connecting distant regions. This pattern did not appear instantly. It grew from tiny differences in density in the early universe. In the next section, we will step back to those first chapters and first light. For now, take a calm zoom-out reset. Picture a dark sky sprinkled with soft points that gather into glowing islands. Those islands gather into chains, and those chains trace a web across darkness. When you picture a galaxy, do you picture a spiral, an oval, or something messy and irregular? To understand today's structure, we step backward to the earliest chapters of the universe. Let's step back in time, not by traveling, but by following old light. The farther we look, the earlier the universe appears. There is one kind of light that is older than any star you can see. It is called the cosmic microwave background, sometimes called CMB. It is a faint glow that fills space in every direction. It is not coming from one place. It is the afterglow of a young universe, stretched and cooled by expansion. Long ago, the universe was hot and dense, like a bright fog. Light could not travel freely then, because it kept scattering off charged particles. As the universe expanded, it cooled. Eventually, electrons and nuclei paired up to form neutral atoms. When that happened, light could finally move long distances without constant scattering. That moment is sometimes described as the universe becoming transparent. The cosmic microwave background is a snapshot from that era. It is ancient light that has been traveling ever since. It is still here now, quietly passing through you and through Earth. You cannot see it with your eyes, but instruments can measure it as microwaves, like a very cold background hiss. This background glow is one of cosmology's calm foundations. It gives a stable reference point, like a baseline hum behind everything else. It is remarkably uniform across the sky, and yet it has tiny variations, like gentle ripples in a smooth pond. Those tiny variations matter because they are the seeds of later structure. They mark places that were slightly denser or slightly thinner than average. Over billions of years, gravity amplified those small differences. That is how a smooth early universe became a web of galaxies. If you like, picture the background glow as a soft wallpaper of the cosmos. Not bright, not loud, just everywhere, always present. Now let's talk about expansion, because it explains why that glow is so cool now. Expansion means space itself is stretching over time. It does not mean everything is flying through space like shrapnel. It means the distance between far apart, unbound regions grows. Locally, gravity can hold things together. Atoms stay the same size. People stay the same size. Planets stay in their orbits. Galaxies can remain bound, and galaxy groups can remain bound. But on very large scales, the average spacing increases. A simple way to picture it is a rising loaf of bread. As the dough expands, raisins drift farther apart. The raisins do not expand, but the distances between them do. In the universe, galaxies are like the raisins. This stretching affects light as it travels. As space expands, light's wavelength can stretch too. That stretching shifts light toward longer wavelengths. Visible light can become infrared, and infrared can become microwave. This is one meaning of redshift. Redshift can also come from motion, but in cosmology it often reflects expansion. When we measure the redshift of distant galaxies, we learn about how space has grown. There is a broad relationship. Farther galaxies tend to show larger redshifts. This relationship is often called Hubble's law. It tells us that recession tends to scale with distance on large scales. The key word is tends because local gravity adds its own motions. Nearby galaxies can move toward us or sideways even in an expanding universe. But at great distances, the expansion pattern becomes clearer. So redshift is a kind of distance clue and also a time clue. High redshift objects are seen as they were when the universe was younger. This is why cosmology often feels like archaeology. We are reading layers of time with light. If you like, take a slow breath and imagine space as a gentle fabric stretching. Not tearing, not snapping, just slowly widening. Now we come to an idea about the very earliest moments. Inflation. Inflation is a proposed period of extremely rapid expansion very early on. It was suggested to explain why the universe looks so uniform across huge distances. It also helps explain why space looks so flat on large scales. Inflation is supported by several lines of evidence, but details are still studied. Cosmologists test inflation ideas by looking for subtle patterns in the background glow. They examine how the tiny temperature variations are distributed across the sky. They also look for faint polarization patterns, which are like light's orientation imprint. Some predicted signals are very difficult to measure, so the work continues. It is a good example of careful science at the edge of what instruments can do. The calm takeaway is simple. Early expansion may have been complicated, and the universe left clues in the oldest light we can measure. Now let's name the main cosmic ingredients, as far as we can infer them. First is ordinary matter, the stuff made of atoms. Stars, planets, your body, and dust clouds are all ordinary matter. Ordinary matter is important to us, but it is not the whole budget of the universe. There is also dark matter, which does not shine like normal matter. We do not see dark matter directly in light. We infer it from its gravity, especially from galaxy motions and lensing. Dark matter tends to clump and form halos around galaxies and clusters. Those halos help ordinary gas gather and cool, which helps galaxies form. Without dark matter, the web of structure would look different. Then there is dark energy, a name for what seems to drive accelerated expansion. It is not a substance we can bottle. It is a description of how expansion behaves at late times. We measure its influence through distances, redshifts, and the growth of structure. Dark energy appears to be smooth, not clumpy like dark matter. So the universe is a mix: atoms, invisible mass, and an effect that speeds expansion. It can sound abstract, but it is anchored in measurable patterns. Those patterns include the background glow, galaxy clustering, and cosmic lensing. If you want a quiet mental picture, imagine 3 layers of influence. Atoms make light and chemistry. Dark matter makes scaffolding. Dark energy changes the pace of the stretching fabric. Now let's move forward a little from the background glow to the first stars. After the universe became transparent, it entered a long dark period. There were no stars at first, just expanding gas and dark matter structure. Gravity slowly gathered gas into denser regions. Over time, the first stars ignited inside early halos. These first stars were likely different from most stars today. They may have been more massive on average because the early gas was simpler. With fewer heavy elements, cooling behaved differently. Massive stars burn fuel quickly. So many early stars were short-lived. Even in their short lives, they transformed their surroundings. Their ultraviolet light could ionize nearby hydrogen gas. Ionize means knocking electrons free again, turning neutral gas into plasma. As more stars and early galaxies formed, ionized regions grew and overlapped. This era is called reionization. It is a kind of phase change for the intergalactic medium. The universe went from mostly neutral gas back to mostly ionized gas between galaxies. We study this era indirectly. We look at very distant galaxies and quasars and how their light is absorbed. We look for telltale drop-offs and absorption signatures along the way. We also use radio observations that can trace neutral hydrogen across large scales. This is difficult work because the signals are faint and foreground noise is strong. Still, the picture is improving, step by step. Reionization is a bridge between the smooth early glow and the structured universe we see now. It is when the first lights began to shape the cosmic fog. And it is part of how the cosmic web became visible in starlight. Now take a calm recap, like a soft closing of a book page. The universe keeps a memory in its background glow, still present everywhere. Space expands, stretching distances and stretching light's wavelength. Inflation is a proposed early burst of expansion, supported but still investigated in detail. Ordinary matter makes the stars we see, dark matter builds the hidden framework, and dark energy affects the long-term expansion. The first stars turned on, and their light helped reionize the intergalactic gas. Does the idea of ancient background light feel comforting or strange? From the universe's first light, we return to the present, where space has weather you can't see but we can measure. Now we return to the present and to something you cannot see but can measure. Space has an environment, like weather, but it is made of particles and fields. It changes with the sun, with Earth's magnetism, and with time. To keep it calm, we will name the pieces and how they behave. First, radiation in space comes in different forms. Some radiation is electromagnetic, like visible light, ultraviolet, X-rays, and gamma rays. Some radiation is made of particles like protons, electrons, and heavier ions. The difference matters because they interact with shielding in different ways. Dose is not one number that applies everywhere. It depends on time, shielding, and solar conditions. It also depends on where you are, near Earth or far from it. A spacecraft in low Earth orbit is partly protected by Earth's magnetic field. A spacecraft traveling to the Moon or Mars is less protected by that field. Now, there are two major sources of high-energy particles to remember. One is cosmic rays, which come from outside the solar system. Cosmic rays are particles accelerated by violent processes in the galaxy, like supernova remnants. Some cosmic rays may also come from even more distant sources. They arrive from many directions, like a steady rain of fast particles. The other source is the sun itself. The sun can send bursts of energetic particles during flares and coronal mass ejections. These are called solar energetic particles. They can arrive quickly and their intensity can vary a lot. So cosmic rays are more steady and solar energetic particles are more event-driven. Both are part of the invisible environment around any spacecraft. Now let's move closer to Earth's natural shield. Earth has a magnetic field that forms the magnetosphere. The magnetosphere is a region where Earth's field guides charged particles. It deflects many solar wind particles around the planet. It is not a perfect wall, but it is a strong dynamic guide. The solar wind compresses the magnetosphere on the day side. On the night side, it stretches the field into a long tail. So Earth's shield has shape like a windswept bubble. Within it, some particles become trapped in belts. These are the radiation belts, regions of charged particles spiraling along field lines. These belts matter for satellites because they can damage electronics over time. Spacecraft designers account for this with shielding and careful orbit choices. Now, when conditions are right, particles can follow field lines down toward the poles. They collide with the upper atmosphere and transfer energy to atoms and molecules. Those collisions create auroras, the soft curtains of light near polar regions. Auroras are the visible signature of invisible space weather. They are a quiet reminder that Earth is connected to the sun. Sometimes the magnetosphere is disturbed more strongly. A geomagnetic storm happens when solar wind conditions strongly couple to Earth's field. This can change currents in near-Earth space and in Earth's upper atmosphere. In extreme cases, geomagnetic storms can affect power grids and satellite operations. But most of the time, the effects are mild or manageable. For many people, the only noticeable result is a chance at beautiful auroras. Now, space weather also affects technology in subtler ways. Satellites orbit through the very top of Earth's atmosphere. That upper atmosphere can expand when it is heated by solar activity. When it expands, it creates more drag on satellites in low orbit. More drag means satellites lose altitude faster unless they adjust. During strong solar activity, operators may track and correct orbits more often. Space weather also affects the ionosphere, a layer of charged particles high above Earth. The ionosphere can bend and delay radio waves, so changes in the ionosphere can affect radio communication and navigation signals. This can matter for high-frequency radio and for satellite navigation accuracy. Most of the time, systems have ways to compensate, but it is another reminder that near-Earth space is not empty and static. Now, not all hazards are radiation. There are also micrometeoroids, tiny grains moving very fast. Even a small grain can carry significant kinetic energy at orbital speeds. In orbit, speed is often kilometers per second, so impacts are energetic. This is why spacecraft use specific shielding approaches. One common method is layered shielding that causes a particle to break up and spread out. The energy is dissipated across layers instead of punching through one spot. Designers also use redundancy, so one small failure does not end a mission. So micrometeoroids are a known risk, but also a managed one. Most spacecraft are built with this environment in mind from the beginning. Now, let's connect the environment to human biology gently and practically. Humans are more sensitive to radiation than electronics in a different way. In low Earth orbit, astronauts still have some magnetic shielding from Earth. They also have spacecraft shielding and monitoring. But deep space is different. Beyond Earth's magnetosphere, exposure to cosmic rays becomes more significant. Solar energetic particle events can also be a concern during certain times. So, deep space missions plan for radiation as part of the schedule and design. They monitor the sun, track conditions, and choose launch windows carefully. Spacecraft may include shelter areas with extra shielding for short-term events. Materials, water, and supplies can also serve as added shielding if arranged wisely. The goal is not to eliminate the environment, but to understand and mitigate it. This is the steady theme of spaceflight: measure, model, and adapt. And the same is true for satellites and astronauts alike. Space is not unsafe in a simple way. It is different, with conditions we do not experience on the ground. Engineers and scientists treat those conditions as numbers, not as fears. They quantify dose, they test materials, and they add margins. They build systems that keep working even when the environment shifts. If you want a calming perspective, notice the steadiness in all of this. The sun changes, the magnetosphere responds, and we measure it continuously. We forecast space weather much like we forecast storms in the atmosphere. We will never control the sun, but we can be prepared for its rhythms. Have you ever seen an aurora in person, or only in photos? Now we trace the quiet milestones of exploration that turn points of light into visited places. If you're replaying this at night, you might turn autoplay off, so the sound stays predictable. And if your app has a sleep timer, setting 1 can help you rest without surprises. With that practical reset, we follow the human and robotic path into space. Now we follow the path of exploration, the quiet way we turn distant lights into places. Space exploration is often pictured as drama and speed. In practice, it is mostly patience, planning, and steady measurement. We begin with robotic exploration because robots are our first gentle touch. A deep space probe is a messenger built to last. It carries instruments, power, and a radio voice, and it keeps going for years. Some probes keep sending data for decades, long after their launch celebrations fade. They travel through cold darkness, returning calm streams of numbers. Those numbers become maps, chemistry clues, and weather stories for other worlds. Robotic missions often move in steps: flybys, orbiters, landers, and rovers. Each step answers a different kind of question. A flyby is a quick look, like passing a window at night. It gives first images, first measurements, and first surprises. An orbiter stays, circling a world again and again. Orbiters turn quick looks into global maps and long-term monitoring. They watch seasons, measure gravity, and trace atmosphere changes over time. A lander goes down to one place and studies the ground directly. It can taste soil, measure wind, and listen to tremors. A rover adds movement, slowly exploring a region like a careful field geologist. These steps are not better or worse, just suited to different goals. Early in the space age, even reaching orbit changed everything. The first satellites showed that space was reachable and measurable. Radio signals from space proved that machines could survive above the atmosphere. Soon, Earth maps improved, weather forecasting improved, and navigation improved. A view from orbit made the planet feel connected and whole. Robotic missions also taught us how to travel far without getting lost. Guidance and navigation are mostly math and repeated checks. Trajectory design is like throwing a paper airplane across a large room, but with gravity assisting. Engineers aim, correct gently, and let physics do most of the work. A small engine burn at the right moment can change a mission's entire path. Often, a spacecraft uses gravity assists, swinging by planets to gain speed and change direction. This is a quiet trick of celestial mechanics, not a violent slingshot. The spacecraft and planet exchange a tiny bit of momentum and the route becomes possible. Robots have visited every planet in our solar system, at least by flyby or orbit. They have watched dust storms on Mars and storms on Jupiter. They have mapped icy moons and studied rings in detail. They have sampled comets and brought asteroid material back to Earth. In many cases, the most important discoveries were not planned. They were noticed by careful instruments and curious teams reading the data. Now we shift to human exploration, which adds life support and human limits. Human spaceflight is more demanding because people need air, water, heat control, and safety. Still, the milestones arrived one by one, each proving a new ability. First came human orbits, showing we could survive and work in space for hours and days. Then longer missions, showing we could adapt and keep systems running. Then spacewalks, proving we could work outside a spacecraft while in orbit. A spacewalk is not a sprint. It is slow, deliberate, and checklist-driven. Every movement is planned to conserve oxygen and avoid mistakes. Later came the moon landings, which proved precise navigation across vast distance. They proved controlled descent, surface operations, and safe return. They also proved that a small crew could live and work in another world's environment. Those missions were built on many test flights and incremental learning. Even the dramatic moments were guided by steady procedure. After the moon era, human spaceflight shifted toward long-duration living in orbit. Space stations became laboratories for biology, physics, and engineering. Living in orbit is less about heroics and more about routine. It is about keeping a complex machine healthy while doing science inside it. And it is about learning what the human body does without gravity's constant pull. Now we arrive at microgravity, where the body adapts in quiet, surprising ways. In microgravity, fluids shift toward the upper body. Many astronauts describe a puffy face and lighter legs at first. It is not swelling from injury, just a redistribution of fluids. Over time, the body adjusts, changing how it regulates blood volume and pressure. This is one reason returning to Earth can feel heavy and tiring. Another major change involves bones and muscles. On Earth, standing and walking constantly load the skeleton. In orbit, that loading is reduced, so the body can lose bone density over time. Muscles can also weaken if they are not used against resistance. That is why exercise in space is not optional. It is scheduled daily, with machines designed for microgravity. Astronauts use treadmills with harnesses and resistance devices that mimic weights. They also monitor nutrition and health markers closely. The goal is to keep the body strong for the return home and for future missions. Vision can also change for some astronauts over long missions. Fluid shifts and pressure changes can affect the eyes and vision temporarily or longer. Researchers study this carefully, looking for patterns and mitigation strategies. Sleep is another area where routine matters. In orbit, the sun can rise and set many times a day, depending on the orbit. So astronauts use schedules and controlled lighting to support a normal day-night rhythm. Light management becomes a tool for health and alertness. The calm lesson is that the body is adaptable, but it prefers consistent routines. Now, let's talk about daily life details that people rarely picture. Food in space is chosen with crumbs in mind. Crumbs can float into equipment or vents, so foods are designed to be tidy. Taste can change in orbit, partly because fluids shift in the head and sinuses. Some astronauts report wanting stronger flavors and different textures. Smell and taste are part of comfort, so menu planning matters more than people expect. Water is precious and recycled carefully. Air is filtered, moisture is captured, and systems run constantly in the background. A space station is a home, but also a machine that must breathe. Much of astronaut work is quiet maintenance. They check filters, replace parts, run diagnostics, and follow detailed checklists. Science experiments run alongside these tasks, from plant growth to fluid behavior. Everything is logged, measured, and repeated, like careful laboratory life. There is also the human side of perspective. Many astronauts describe the overview effect. It is a shift in feeling when viewing Earth from space. They report a calmer sense of connection and a clearer sense of scale. Earth can look delicate, bright, and borderless from orbit. That view can make daily worries feel smaller without making them unimportant. It can be a quiet kind of awe, not a loud one. Now we turn to a few unusual discoveries that feel unreal, yet are observed. One category is interstellar visitors. These are objects that pass through our solar system on paths that do not loop back. Their trajectories suggest they came from outside the Sun's family. They move too fast and their orbits are not bound to the Sun. We have observed at least a couple of such visitors in recent years. Each one is brief, like a traveler passing through a station without stopping. They hint that other star systems also shed debris into interstellar space. Another category is fast radio bursts. These are brief flashes of radio energy seen from distant parts of the sky. They last only a short moment, then vanish. Their origins are still studied, with several leading ideas and ongoing debates. Some are linked to distant galaxies, and a few have been traced to repeating sources. This is an area where discovery is active, and explanations are still refined. The calm takeaway is that the universe still has new signals to offer. There are also rogue planets, planets not clearly bound to a star. Some may have been ejected during early gravitational reshuffling. Others may form in unusual ways, still being investigated. We infer them through subtle effects like microlensing, not through direct pictures. Rogue planets remind us that orbits can be rearranged and systems can be messy. We also find planets around unexpected stars, including very small stars and dense remnants. Nature uses many pathways, and our solar system is only one example. Now we look forward to what comes next with slow steps rather than leaps. One major future chapter is better telescopes. New observatories aim to see earlier galaxies, closer to the first star eras. Others aim to probe exoplanet atmospheres with more sensitivity. They will search for patterns in gases, clouds, and temperature structure. This continues the theme of learning from tiny signals. Another chapter is returning to the moon, not just to visit, but to operate. Moon surface work is practiced for longer missions farther out. It teaches dust management, thermal extremes, long nights, and power planning. It teaches how to build routines in a harsh environment. Those routines matter more than dramatic moments. They are the difference between a short visit and a sustained presence. It is also a chance to use the moon as a science platform, quiet and stable. Now we close an open loop from earlier in the video. Earlier, we promised one distance that is easy to picture and why it changes every day. That distance is the distance to the moon. We can picture the moon as a companion in our sky, always within reach of imagination. But the moon's orbit is slightly elliptical, not a perfect circle. So the moon is sometimes a little closer and sometimes a little farther away. This changes its apparent size subtly, and it changes the exact distance daily. We measure that distance with lasers bouncing light from reflectors on the moon. The same method also measures the moon's slow recession over time. So a familiar object becomes a precise ruler for celestial motion. That is the quiet beauty of exploration. Wonder becomes measurement without losing wonder. Before we transition, take a slow breath and let the timeline settle. Robots fly first, mapping and tasting from a distance. Humans follow with routines, training, and careful life support. Bodies adapt, technology adapts, and our understanding grows in layers. If you want, name one discovery that felt most calming or most surprising. And if you leave a timestamp in the comments, it helps others find that moment again. In the final minute, we'll gently summarize the biggest patterns across everything you heard. If you want more long, steady science like this, you can subscribe. And if you'd like a follow-up, comment deep dive plus your topic. For example, exoplanet atmospheres, black holes, or the history of space missions. We'll end on a slow fade with no sudden change.